Thank you. Yeah, so I'd first just like to start by saying thanks so much to Prism and to Claire for inviting me here today. It's a real pleasure to speak in front of such a wonderful group of people, so thank you. My name's Charlie, my pronouns are she, her, and I'm a third-year PhD student at the University of Exeter. And my PhD work is in the field of open quantum systems. And today I'm going to talk to you a bit about how this can actually link to identity. So let's just get straight into some quantum mechanics to cheer everybody up. So you never hear that. So what do I mean when I say open quantum systems? So actually, forget open and quantum for now. Let's just think of a system. So the system that we'll be considering is, for example, a hot coffee cup. I love coffee, so it's going to be a running theme throughout the talk. Now, unfortunately, this hot coffee cup doesn't stay hot forever, especially if you're like me and you're prone to leave it out and forget about it, and then have to make yourself another, and then you end up with 10 on your desk. But yeah, so this doesn't stay hot forever. Now, why? Now, this is because the hot coffee cup is actually in a colder room. And together, the system and the environment form an open system. So, classically and on the macro scale and in our everyday lives, physicists can actually describe really well how the coffee cup cools down. And we can do so using the laws of thermodynamics. So we know that the conservation of energy says that if we lose a certain amount from the system, the hot coffee cup, that'll be gained by the environment and they'll eventually reach thermal equilibrium. Also, we know from our everyday experience that the heat flows from hot to cold. And that's the second law. So we can describe this really well. And actually, an important thing is that we don't actually have to worry too much about the form of the interaction between the system and the environment to describe the heat flow well. So what if we scale it down to the atomic scale? So we no longer have a regular coffee cup, we now have a quantum coffee cup. So can we describe I suppose the way the system interacts with its environment and the heat flow using similar ideas from before? And this precise question is what led to the, I suppose really the development of quantum thermodynamics, which seeks to unify thermodynamics with quantum mechanics and trying to understand these thermodynamic ideas that work so well in our everyday lives from a quantum perspective. So this is quantum thermodynamics. And it's a very active area of research, and colleagues of mine are really working in it and producing some really interesting results. Now, importantly, on the quantum scale, so whereas before I said that we don't have to worry too much about the form of this interaction, quantum mechanically, because we've scaled down our system to a really small size, any sort of noise from the environment will suddenly get amplified. So we actually do have to worry about the form of this interaction. So yeah, as I've just described, this is an open quantum system. So we've introduced this idea of open quantum systems using our hot coffee cup analogy. But where else might we want to try and understand how a quantum system interacts with its environment? One such place is in the world of magnetism. Now, recently, as experiments have been getting better and better, the classical equations that we use to describe how magnets work actually don't always predict what we're seeing in an experiment. And it's suggested that perhaps what's going on is we need to actually be able to account for quantum effects in these materials. So to introduce this idea, I'll briefly talk a bit about, give quite a crude description of how magnets work. So if we zoomed into the magnet, just to the sort of the scale of a few atoms, we'd sort of get the following picture. Now, to understand how magnets work, what we actually need to think about is the electrons of the atoms that make up the material. Now, each of these electrons, you can think of, well, classically as spinning around the atom. And because they spin around, they have something called angular momentum. So you can think of that as, using the coffee analogy, if I have a coffee grinder, I'm spinning it around, the faster I'm spinning it, sort of turning it around, the more angular momentum it has. So classically, this angular momentum can take any value from 0, so it's not spinning at all, to, well, however big you want, and anywhere in between. Now, quantum mechanically, this isn't the case, and the angular momentum can only have set values. And this is what we call quantization. So all quantum really means is small indivisible units. So when we talk about quantizing the angular momentum, it's just letting it have specific discrete values. and that's what we call spin. So really the point of this little discussion here was to say that we care about the spin to be able to sort of help describe how magnets work. So another important thing actually to mention will be that because the electron has a charge, it's negatively charged, and it's moving, each of these spins is like a little magnet. So on average, all these little magnets point in different directions, and it will cancel out. But if we apply an external magnetic field, we can actually get all of these spins and their sort of mini magnets to line up with each other, and we get a net magnetic effect. So that's a bit of an insight into how magnets work. And we've seen how important these spins are to describe that. So naturally, as I was talking about open systems, we want to understand how these spins interact with their environment, because this might hold some information on what those classical equations maybe were missing. So because we're physicists, we're going to simplify it down and just consider a single spin for now as our system, because it turns out to be really difficult to fully simulate a system of a lot of spins quantum mechanically, and some of you in the audience are laughing because you also know the problem. So for now, we're going to consider that single spin. And as I just mentioned, that single spin is in an environment. So it's an open quantum system, such as the hot coffee cup we had before, but now we're just looking at two things. Well, the environment is just at some constant temperature. So normally when people talk about open systems that involve a spin, they just couple the spin to one environment. And in many situations, this is a good model for the physics. But actually, in the magnetic world, it makes more sense to actually couple the spin to not one, but to three environments. So our model is now going to look something like this. So a single spin coupled to three independent environments. Now, the first real question of the project was, what difference does changing the theoretical model from having one environment to three environments make? And we need some way to kind of quantify this. And what we're going to use to quantify this is the entanglement between the spin and its environment, which naturally leads me on to entanglement. Now, this is where the quantum fun really starts. So in quantum mechanics, we can know everything about the state of the system and the environment together with complete certainty. But we can know nothing about the system state on its own or the environment state on its own. And this is quite weird, right? Because classically, if you knew the state of everything, you'd also know the state of the system and the environment together, individually rather. So this is kind of what we mean when we're talking about entanglement. These two are related to each other. So really, this is where it first links back to the title of my talk. You can't describe what's going on as just a sum of parts. You really need to look at the whole picture. And this is where my prop comes in. So you can think of it as follows. So I've got a jar here that I nicked off my partner, so I'm using your coffee. So we've got the coffee and the jar. And classically, if I told you it's over here, then you know where the coffee is, and you know where the jar is separately. But quantum mechanically, just because you know the jar and the coffee's over here, it doesn't tell you anything about, or doesn't necessarily tell you anything about where the coffee is or where the jar is on its own, which is quite weird. And I'd be lying if I said I fully understand what's going on, and I feel like a lot of the physics community is probably the same. But anyway, so we want to see what happens to the entanglement between these two models. And what we find is that actually, just by coupling a single spin to multiple environments, we can increase the amount of entanglement between the spin and its surroundings, which is kind of a bit, maybe not necessarily intuitive. Furthermore, you may say to me, well, Charlie, but we're coupling to three environments, so maybe there's more entanglement, maybe it is intuitive. But that's not how entanglement works. Like many things in quantum physics, it's very counterintuitive. And indeed, you can't just sum up 3 times the single interaction to recover what we see on the right. So for the second time, we're seeing that you can't describe it as a sum of its parts. So enough physics for now. And I'll just wrap up and then get on to the next bit. So we all interact with our surroundings, and quantum systems are no different. And on the quantum scale, one thing I really want to sort of, as a take-home message, is that this interaction can be really, really important, and we can't neglect it. And in many cases, we need to consider the system interacting with more than one environment to actually model the physics and what's going on. And an example that I've introduced here today is about magnetism. Now, coupling to quantum spins to more than one environment can also lead to some really cool effects, such as an increase in entanglement. So there are some cool things that come out of this. And this can't be understood simply as a sum of parts approach. So I did promise that the physics would end, and now I'm going to talk a bit about how we can link this idea of open systems to our identity. So a bit about me. So I grew up in the southwest of the UK, just outside Bristol, where I went to school. And I kind of always knew I wanted to do physics or some science of some sort. And yeah, I did sort of A-levels in the sciences and decided then that I wanted to do physics at university. And that brought me to Exeter in 2017, where I started my undergrad degree, my integrated masters. And I had a really sort of good 4 years of doing some fun physics. But in particular, it was in the final year that I got first introduced to this idea of having what an open quantum system is. And I actually did my master's project in that field. And as was said at the start, it was looking at a bit sort of going back to what I first introduced, the heat flow stuff. So I was trying to understand how we model that on the smallest of scales, which is very important for like quantum tech and stuff nowadays, where we really need to be able to characterize that interaction to get our devices to work. Yeah, so I graduated in 2021. Well, sort of. I actually graduated in 22 when all the COVID stuff was kind of washed over a bit. But yes, so I graduated in 2021, and I was lucky to be able to actually start a PhD in the same sort of field here, also in Exeter. And yeah, I've been there ever since. So whilst things were going relatively smoothly academically, as smoothly as doing a degree sort of can go, I did come across some hurdles, I think, throughout the years, and there was a lot of sort of self-discovery. So in 2018, that's me, my sort of my Pride Maker-thon, I came out as gay. And really, I should say there's some quantum fuzziness going on here because it was all a bit blurred. It was a long sort of process, but it got to the point where I realised that not being sort of openly true to myself was causing me quite a bit of distress. But I was very lucky to be supported by a really, my family and friends were wonderful in that time. So I came out as gay in 2018-ish. And then something else that happened. So after I started my PhD, I realised that I was kind of struggling with work a bit, and it'd been the first time I'd really sort of encountered these proper difficulties. And I think it was suddenly there was a shift from doing shorter term kind of projects and having really clear deadlines to suddenly having this big open-ended question. And you were meant to be much more sort of self-directed. Even though I do have great support at uni, it was still, it's still on you to kind of guide your work. And through this, I kind of realised that maybe my brain worked a bit differently. And so in 2023, I got my ADHD diagnosis. And since then, I've been able to kind of put into place, some methods that help me work a bit better, and it's really sort of shed light onto a lot of my past experiences as well. So it's been great to be able to kind of understand myself a bit better. And then just when I thought kind of, I'd understood myself, I started to question my gender. I say started to, it sort of had gone on quite a while, but I'd not quite realised that that's what was going on. I'd always been labelled as a tomboy and hated wearing dresses, but I thought, maybe that's just, well, everybody feels. But it went deeper than that. I knew that to my core, it wasn't just I didn't like wearing them, it was quite uncomfortable or really quite distressing. And it's through, social media can be very toxic, but in many ways it helped me to connect with other people who felt in a similar way to me. And also these wonderful events, the Prism events, also helped me to connect with other people. And I realised that actually maybe there was something that described my experience quite well, and that was being non-binary. So I suppose this is kind of the first public sort of space I properly talked about it. But yeah, so there was quite a lot that went on in those few years. And there are lots of... No, it's fine. Yeah, no worries. That's okay. And there are lots of parts... I look back at this and I think there are lots of parts and lots of things that are going on. And maybe, it's a bad segue here, but we're trying. Maybe I'm an open quantum system. So there are lots of parts of me that I've talked about. So There's the physics, so it talks a lot about my work, and obviously I work with some wonderful people. And that's a big part of sort of who I am. Also my identity as a gay and non-binary person. This here is the one of the Pride sort of crossings in Bristol. So that's a big part of who I am. Also, I love to run, I love to climb, and I've got lucky to have a lovely sort of group of my family and friends around me, and my wonderful partner Lily's here today, so thanks Lils. And sorry I borrowed your copy. And I couldn't make a talk without talking about my lovely dog here at Oslo, sporting a lovely sort of pride bandana. So yeah, so I think actually trying to understand myself just as the individual parts really kind of didn't represent my authentic self very well, and taking this sort of approach, this global approach of looking at me as a whole system did. So maybe that's something that others can also relate to. So some final thoughts before we wrap up. So just like quantum systems, we're inextricably linked to our environments. And maybe we can model ourselves as an open system with many parts, and it's not just a bad attempt at linking the two, but maybe we can, and really this has helped me to kind of understand myself a bit better. And often, as I've just said, we need to look at the whole picture to properly describe ourselves. And when we do, just like with quantum systems, when we describe the whole picture, we get cool things like quantum entanglement. We also find something wonderful when we take ourselves and our whole picture. It's what makes us all sort of unique and no two people the same. And just before I wrap up, I have to acknowledge and want to acknowledge my wonderful PhD supervisors, Simon Horsley and Janet Anders at the university. And I mentioned my master's project work, and that was supervised by Luis Carrera, who was at Exeter at the time and is now in Tenerife. And this work was from this paper that we've just put out, just being able to publish, and that was done in collaboration with my supervisors, a colleague of ours, Jim Crasser, and my wonderful postdoc and good friend, Feather Cherisola, who's in the audience as well. So thank you, Feather, you've been of great support. And yet you can find it on the QR code here if you really want to do that, that's fine. And with that, I thank you for your time, and I'm happy to take any questions. So thank you.
Excellent, thank you very much.